2 million years ago, a group of humans stood up, left Africa, and changed the course of humanity forever. A population once constrained to the confines of one continent made their way east toward new and unpredictable environments. This was a group of what we now call Homo erectus. Homo erectus is known for many things. Anthropologists often consider it the first upright man, or the first truly human species more generally. It is also the most successful human species, having existed for approximately 2 million years. It is all of these things, but it also holds the title as the first human species to leave Africa. But why this species and not the earlier Homo habilis, or even earlier yet, Australopithecines? The human lineage had been evolving in Africa since roughly 7 million years ago, so why wasn't it until Homo erectus that new territories were explored? Today, we'll be answering these questions and uncovering the secrets that set Homo erectus apart. We'll discover what made Homo erectus so special, specifically, its suite of physical, cognitive, and social adaptations that allowed it to make such long journeys away from home. Who were these ancient explorers? How did they conquer vast distances? And what became of them as they ventured into the furthest reaches of the ancient world? Let's find out together. In 1891, Eugene Dubois, a Dutch physician turned paleoanthropologist, made the discovery of a lifetime. He had traveled to Indonesia in search of what German evolutionary biologist Ernst Haeckel argued was the first human species. Dubois and Haeckel belonged to the camp that believed Asia, not Africa, was the origin of humanity, and even went so far as to name that very first species before it was even discovered. Haeckel named it Pithecanthropus, which translates to ape man. Their argument was rooted in the anatomical similarities they observed between humans and the Asian great ape, the orangutan. After not finding any luck on the island of Sumatra, Dubois shifted his focus to Java. He caught wind of some bones that were eroding out of the Solo River near the village of Trinil. He and his crew began excavating that site, and by the end of the year, they had their smoking gun. They recovered a human molar, a skull fragment, and a complete femur bone. The skull was clearly not that of a human with its massive brow ridge, but it was too big to belong to a non-human primate. Dubois deduced that they had discovered their Pithecanthropus, to which he added Pithecanthropus erectus. They also gave the specimen the nickname of Java Man. Java Man marks the first Homo erectus to be pulled out of the earth, and at the time, the oldest human bones. Though significant in and of itself, it did not age well with regard to human origins. There was a sampling bias in archaeology. Simply not enough ground had been excavated to make such conclusions, especially in the African continent. Upon further archaeological investigations throughout the 20th century, we came to learn that although Java Man did belong to the species Homo erectus, Indonesia was not its place of origin. In the other African origin camp were figures like Charles Darwin himself, who said, "In each great region of the world, the living mammals are closely related to the extinct species of the same region. It is therefore probable that Africa was formerly inhabited by extinct apes closely allied to the gorilla and chimpanzee. And as these two species are now man's nearest allies, it is somewhat more probable that our early progenitors lived on the African continent than elsewhere." Excavations of Homo erectus throughout the African continent in places like Olduvai Gorge, Lake Turkana, and Kubifora have revealed some of the oldest Homo erectus remains, dating back to around 1.9 million years ago. These discoveries, in addition to even older species like Homo habilis and the Australopithecines, which are confined to Africa, have resulted in a consensus favoring Darwin's perspective over Haeckel's. Among all of these ancient hominins, however, Homo erectus is the anomaly. Its origins are in Africa, but it's also been found across the Old World. Java Man is just one example of this. Erectus remains have been unearthed in Kokabus, Turkey, Zhoukoudian Cave in China, Dmanisi in Georgia, and even Mauer in Germany. With such a broad geographic distribution of the species, variation in size and shape is to be expected, but some anthropologists go as far as to claim that all of these variants represent subspecies. These include taxa like Homo erectus ergaster, Homo erectus georgicus, and Homo erectus soloensis. Without going too far into the weeds, this just represents the age-old scientific debate of lumping or splitting with regard to how we define a species. In all likelihood, these variations simply represent populations of Homo erectus that were gradually adapting to their local environments. That said, there are enough commonalities among them that we can identify them as wholly separate from other human species. So what are the defining features of Homo erectus? What defines Homo erectus is the culmination of traits that eventually led not only to their dispersal out of Africa, but to defining our own species, Homo sapiens. In the following sections, we'll explore exactly what these are, how they enabled erectus to reach Europe and Asia, and how our modern human form still embodies such characteristics. It's quite odd that humans voluntarily engage in bouts of extreme physical activity, not motivated by survival. It's rare, almost unheard of, for a wild animal to run a marathon, let alone without the end goal of a tasty meal. We will run simply for the sole purpose of running itself. Homo erectus may not have been running to win gold, but they were certainly walking and running long distances. Their ability to do so was a key factor responsible for their migrations out of Africa, and we can find evidence of it in their bodies. The body plan of Homo erectus was much different from that of earlier human species. It was adapted for endurance. Species that predated Homo erectus, like the various Australopithecines, were not totally bipedal yet. They retained some traits for arboreal living, like having longer arms than legs. Homo habilis had longer legs than them, but still their arm-to-leg ratio was not significantly different. Homo erectus is the first hominin species we see with longer legs than arms, a step toward modernity, no pun intended. It was also taller than other hominins. Estimates suggest that Homo habilis was about 4 feet tall, while Homo erectus was roughly 5'9", and some individuals were surely around 6 foot. These traits point to a species fully committed to living on the ground, adapted to efficient bipedal locomotion. Longer legs increased stride length, meaning Homo erectus could cover more ground with each step, reducing the energy cost per unit of distance. This efficiency was crucial for traveling between distant resource patches, such as water sources or hunting grounds. Building upon these anatomical observations, we now have archaeological evidence of footprints that have come to similar conclusions. The 1.5 million-year-old footprints found in Illoret, Kenya, made by 20 or more individuals, point to the oldest direct evidence for modern human-like weight transfer and confirm the presence of an energy-saving longitudinally arched foot in Homo erectus. In these footprints, we can also see the anatomy of the big toe, one that is no longer opposable and is aligned in a modern position that enhances balance and stability. In a pivotal paper published in 2004, Dennis Bramble and Daniel Lieberman argue that the Homo lineage, and erectus in particular, is adapted for long-distance locomotion. They dive deep into the anatomical and physiological adaptations associated with such behavior, including those aforementioned. Some additional important observations include an elongated, narrow waist, and lower, wider shoulders, which help counterbalance hip rotation with the swinging of our arms. Further physical adaptations that aid in endurance locomotion, which likely appeared around the time of erectus, include those associated with things like thermoregulation and respiration. Sustained running generates heat within the body that must be dissipated, or else you could overheat and die. Some derived features in humans that help with this are our reduced body hair, increased sweat glands, and mouth breathing. It's likely that these were present in erectus, but we do not have the physical evidence. One study has even suggested that these hominins could run for up to 5.5 hours before reaching their dehydration limit. To conclude, Bramble and Lieberman say most of the major structural bases of endurance running that can be observed in the skeleton are present in early Homo erectus. And lastly, we can take a look at a fascinating paper that was just published in 2025, looking specifically at the running abilities of a more ancient hominin, Australopithecus. Pithecanthropus afarensis. Bates et al. Created a running simulation for afarensis based on bone anatomy and inferred muscle architecture. They found that the maximal speed and endurance range for this species were significantly lower than more recent hominins, which suggests that key features in the human body plan evolved specifically for improved running performance. All of this points to a species that found a uniquely human niche. Every animal in the natural world has its set of advantages and disadvantages. Cheetahs are lightning quick, hyenas organize in groups, and raptors have lethal talons. Humans, especially as we became more modern, were not particularly strong or physically intimidating, but we could run long distances. This advantage, emerging with Homo erectus, gave us the edge when hunting for prey. We call this persistence hunting, and it's what humans became especially efficient at. Persistence hunting is running your prey to exhaustion. Although they may be faster than you, if you possess greater endurance, then you will outwork them in the long run. If you can't beat your prey in a sprint, you have to beat them in a marathon. It's a foraging strategy used by human hunter-gatherers even through modern times, and it most likely started with Homo erectus. So what does this all mean? Well, the physical world places great constraints on all species, and humans are no different. With sufficient adaptations, those limits can be lifted a little bit. Species prior to Homo erectus were physiologically more limited in their capacity for long-distance travel. All of these physical adaptations evident in Homo erectus were the prerequisites for surpassing the limits of Africa. In conjunction with the following cognitive and cultural breakthroughs, Erectus became a true force to be reckoned with, expanding its territory almost indefinitely. Before exploring what those cognitive and cultural breakthroughs are, I quickly want to shamelessly plug my free newsletter. If you subscribe to the Point 2 newsletter in the description, you'll get access to my archaeology cheat sheet, an essential resource for anyone learning about archaeology online. Additionally, you'll get notified on new Evolve Point 2 videos and access to future content and helpful resources, including my upcoming eBook, Archaeology 101, The Basics. If you find my content valuable, I promise you won't regret it. And with that out of the way, let's explore the psyche of Homo erectus. Unfortunately for us, thoughts don't fossilize. Since brains are made of soft tissue, they don't either. But our brains are encased in skulls that do fossilize, and this gives us only the faintest idea of the cognitive power of ancient humans. The skulls of the archaeological record tell us a story of relatively consistent brain growth throughout human evolution. Over time, brain size has gradually increased both across species and within individual species. Then there are certain periods of punctuated growth. Biological anthropologist Richard Wrangham suggests there are 4 in particular. We'll explore his theory as to why these brain increases occurred later in the video. For now, just know that the emergence of Homo erectus represents one of these marked growth periods. Ancient skulls are measured in cubic centimeters, or cc's, which measure a skull's volume or cranial capacity. This gives us a rough idea of how large the brain encased in that skull would have been. The cranial capacity of Homo habilis ranged from 507 to 690 cubic centimeters. Homo erectus, on the other hand, ranged from 725 to 1,125, approaching volumes seen in modern humans. It's easy for us to look back in hindsight and assume that bigger brains are inherently better, but that is not so obvious. Big brains come with pretty serious costs. For example, they pose issues immediately from birth and even before. Primates with bigger brains have longer gestation periods. Larger heads are harder to birth, potentially threatening the life of both the baby and the mother. Once born, it takes longer for those big brains to fully mature, leading to prolonged infant dependency periods. Once the brain fully matures as an adult, it comes with a high metabolic cost. The brain is the most energetically costly organ in the human body. It burns through calories faster than anything else. In addition to persistence hunting requiring efficient thermoregulation, larger brains that burn more energy also pose a cooling problem. So there are certainly evolutionary costs associated with these big brains that really take off with Homo erectus. Some have argued that genetic drift could explain the evolution of hominin brains, but it seems as though evolutionary advantages would be necessary to offset these costs. Therefore, a good argument could be made that the size increase is more likely to be adaptive than the product of sheer chance. We must then ask, in what ways are big brains adaptive? This is tricky to answer because the brain has so many functions, from unconsciously controlling breathing to creating higher level abstractions. These different functions are typically associated with distinct regions in the brain. The more automatic functions are typically located within the lower, more evolutionarily ancient parts of the brain, while more complex cognition is associated with higher, more recent regions. Research suggests that in humans, certain regions grew more while others lagged behind. For example, humans aren't known for having a great sense of smell, which is reflected in the regions of our brain associated with processing smell. Known as the olfactory bulb, this part of the human brain did not scale up to the same degree as others. In contrast, there is good research suggesting that areas of the prefrontal cortex and neocortex have scaled up to a greater degree than expected for a primate our size. These are precisely the areas of the brain we attribute to higher level thinking, the types of thinking we attribute great importance to in humans. The prefrontal cortex, for example, is associated with advanced executive functions like decision-making, problem-solving, self-control, and planning for the future. It allows us to weigh options, delay gratification, and consider long-term consequences, abilities that are essential for surviving in complex and unpredictable environments. This part of the brain is also crucial for social cognition, enabling empathy, understanding others' intentions, and navigating intricate social dynamics. The neocortex, the outermost layer of the brain, is involved in sensory perception, spatial reasoning, and conscious thought. In humans, the neocortex supports language, abstract thinking, and creativity, which have been key to our success as a species. This scaling up of the neocortex is thought to underpin our ability to develop technology, create art, and build civilizations. In addition to these regional expansions, larger brains in general result in greater networks of connection between areas. Accordingly, anthropologist Thomas Schoenemann says, increasing brain size leads to increasingly complex processing within areas, greater degrees of autonomy between areas, and greater complexity of the possible interactions between areas. This leads to a greater complexity of possible network activation states, which is equivalent to a greater degree of conceptual subtlety and sophistication possible in the organism's representations of reality. An interesting area of research I've stumbled upon related to Homo erectus brain evolution deals with dopamine. It seems to be a hot topic nowadays, especially in the world of productivity and quote-unquote biohacking, but it may be an important part of our story here. Dopamine is a neurochemical that plays a key role in reward, motivation, pleasure, and regulating movement. It's been hypothesized that an uptick in dopamine consumption could have occurred alongside increases in meat consumption typically associated with Homo erectus, influencing an expansion or elaboration of the neural systems that mediate this chemical. As such, a host of behaviors related to dopaminergic functions, such as novelty seeking, goal achievement, sociality, and even REM sleep, may have become more prominent in Homo erectus. In addition to meat consumption, increases in physical activity associated with persistence hunting could have had similar effects, given that we now have evidence that exercise increases dopamine levels. The novelty-seeking and motivational attributes of dopamine are particularly important when considering the expansion of Homo erectus out of Africa. Suppose the physiological adaptations discussed earlier provided erectus the physical capacity to engage in long-distance travel, and the cognitive advantages of large brains provided the ability to problem-solve in and adapt to novel environments. In that case, an increase in dopamine may have conferred the underlying motivational states to pursue migrations into new and unfamiliar territories. These are the biological advances we see in Homo erectus that largely separated it from ancestral species. Yet, there were aspects of their lives outside of their bodies that also must be considered, or else the story is incomplete. So let's move on and explore the tools and sociality of these ancient humans, which also allowed them to move beyond the confines of Africa. If you'd like a deeper dive into the evolution of the human brain, I'll leave a link to my video on it in the description. We are now obligate tool users. As individuals in our natural state, we are frail and easily outcompeted by the rest of the animal kingdom. However, the tools we depend on for our survival have placed us at the top of the food chain. Our apex predator status, enabled by these tools, likely became established with the rise of Homo erectus. Erectus lived during a period we call the Paleolithic, which means Old Stone Age. It's typically divided into lower, middle, and upper, each marked by different stone tool technologies. The complexity of these tools generally increased as humans progressed from lower to middle to upper. The lower Paleolithic lasted from around 3.3 million years ago to roughly 300,000 years ago, and Homo erectus's tools represent the pinnacle of this period. The earliest stone tool industries of the lower Paleolithic include Oldowan and Lomekwi choppers. These were big, clunky cobbles with large chunks broken off to create a single sharp edge, typically using another rock. They seem crude when they're compared to later technologies, but they still mark the ability of ancient hominins to construct tools. Other primates, like macaques and orangutans, have been observed using natural objects as tools to acquire food, but actually modifying tools to increase their efficiency is uniquely human. These earliest choppers are generally attributed to Homo habilis, with some researchers suggesting species of Australopithecus were using them too. Taking these tools to the next level, Homo erectus developed the Acheulean industry. What made Acheulean tools so transformative was an extra layer of complexity in the shaping process. Rather than single-edged, often asymmetrical cobble choppers, Acheulean tools are defined by their double-edged symmetry. They created hand axes through bifacial flaking, meaning both sides of the stone were carefully worked to create its sharp edges. This required considerably more planning and skill than other stone tools, suggesting significant cognitive advancements took place. Diaz-Martina and colleagues present a set of cognitive traits that, when aligned with the higher-level goal of creating an Acheulean hand axe, help us understand the mental state of Homo erectus nappers. These include the following: cognitive control, or the ability to stay on task and inhibit automatic responses to distractions or other tasks. Visual spatial cognition, in coordinating the size, edge curvature, and symmetry of the tool. Aesthetic cognition, associated with that symmetry. And categorical information, or the ability to conceptualize something as a tool. Building upon this, experimental studies have recorded the brain activity of modern people making Oldowan and Acheulean tools. Accordingly, they've found differences in the brain networks associated with each. Our findings suggest that Oldowan tool manufacture relies on the coordination of visual attention and motor control to successfully remove simple flakes. It would not be surprising to find that a homologous cognitive network is active in wild chimpanzees when they skillfully crack nuts with stone tools. These same researchers go on to explain the more human cognitive requirements for napping an Acheulean hand axe. Acheulean tool manufacture, in addition, requires the integration of higher-order motor planning, working memory, and auditory feedback mechanisms to attend to information from multiple modalities, as the toolmaker coordinates the different goals required by this more complex task. Tool construction was clearly one domain where Homo erectus applied their new big brains. In conjunction with their persistence hunting niche, Erectus would become uniquely adapted to long but efficient hunting strategies. After catching their prey, these hand axes would speed up their food processing, as evident in butchery marks at various Acheulean archaeological sites. The Box Grove horse butchery site in England shows the temporal and geographic extent of this form of Acheulean utilization. Here, archaeologists have found large horse remains with evidence of bone defleshing and marrow extraction, in association with Acheulean tools. Additional butchery sites have been discovered all around the Old World, from Tanzania to Spain, showing these tools migrating alongside their creators. Another technology employed by Homo erectus was the use of fire. Arguably the most important innovation in human evolution, maybe only second to the stone tool, controlling fire came with a whole host of advantages. First, we can bring this back to Richard Wrangham, who we discussed with regard to his theories on human brain evolution. Wrangham believes that the 4 most drastic expansions of the human brain occurred alongside new eating behaviors, including those associated with fire. The first increase from a chimp-like ancestor to the Australopithecines was likely due to the incorporation of roots and tubers that were more digestible than fiber-rich foliage. Next, the transition to Homo habilis was linked to the adoption of more meat and simple food processing, like butchering carcasses with stone tools. This continued through the era of Homo erectus, who in turn also began controlling fire. This allowed erectus to cook their food. Lastly, the increase in brain size associated with Homo sapiens and the like are attributed to improvements in cooking methods, including earth ovens, containers, pottery, etc. Why was cooking so important? And possibly the catalyst for the most important increase in brain size. Put simply, it increases the caloric energy available in food while decreasing the caloric energy required to digest it. This means that more energy was available to fuel their brains, which were being selected for due to their evolutionary advantages. Various other advantages of fire usage include some of the following: more time, freed up from not having to spend as much time chewing and eating food. It removes pathogens from food. Increasing social bonds may have resulted from cooking together. And lastly, fire serves as protection from the environment, likely providing warmth in the cold and keeping predators at bay. While it likely began with opportunistically coming across natural fires in the wild, Homo erectus eventually learned to start and control fire. When this happened is not exactly known, but some evidence points to intentionally utilized fire dating back to over 1 million years ago in South Africa. Just as humans today are not born instinctually understanding how to nap a stone tool or start a fire, the skills of Homo erectus were learned through the cultural transmission of knowledge. As groups huddled around the fire for safety or shared cooked meals, they likely developed stronger social bonds and more complex interactions. This communal behavior may have laid the groundwork for the more intricate social structure that defined humanity. Firelight extended the day, providing opportunities for storytelling, teaching, and strategizing, activities that would require advanced communication skills and cooperation. Although we don't have solid evidence of language in Homo erectus, it is not unreasonable to suggest that they may have used a form of proto-language consisting of physical gestures and simple vocalizations. Homo erectus was likely a very social species. The analysis of the 1.5 million year old footprints discussed earlier showed us that the group who made them encompassed at least 20 individuals and was composed of multiple males and females. It's possible that this could represent evidence of early humans of the same sex working in cooperation with one another, as opposed to a species of single male, multi-female groups where the men are in constant competition for female mates. The authors of this study said that these data are at the very least consistent with the hypotheses that Homo erectus had a group composition and dynamic that could have supported the emergence of human-like social behaviors, such as patterns of increased cooperation and sexually divided foraging behavior. Cooperative feeding and breeding were pivotal social adaptations that may have arisen with Homo erectus, providing significant survival and reproductive advantages. Sharing food, particularly high-quality resources like cooked meat and plants, reinforced group cohesion and interdependence. This communal effort ensured that all group members, including vulnerable individuals like juveniles or the injured, were nourished, enhancing overall fitness and resilience. In breeding, cooperative care likely played a crucial role in offspring survival. Homo erectus exhibited traits like larger brains and extended juvenile dependency, which required substantial parental investment. Cooperative breeding, where group members like siblings or unrelated individuals helped with child care, would have alleviated these demands. This strategy increased reproductive success, supported larger groups, and enabled Homo erectus children to learn from a wide variety of individuals from within the group. Through observation and imitation, the plastic, growing brains of young generations could adopt the skills necessary to adapt to the environments their species would soon inhabit. If there's any one thing to take away from this video, it's this. There is no single reason why Homo erectus was able to conquer lands untouched by earlier humans. Homo erectus represents an entire panoply of physical, cognitive, and social characteristics that not only allowed it to adapt to various new environments, but that are also present in us today. This adaptability made it the longest-lived human species we're aware of. With that, I want to leave you with a question. Will we outlast their 2 million year record? Or will we succumb to our own demise? Let me know in the comments below. Hope you enjoyed, and if you did, check out the video on the screen. See you in the next one. Stay curious.